Hello everybody, welcome to our last lecture in Math 141. I know, don't cry, I'm trying to hold it together myself. But for real, what I do want to say is that it was an honor being your instructor this quarter, and because of the unfortunate circumstances, I was never able to meet any of you, which kind of deeply saddens me. One of my favorite parts of this job is being able to interact with students. I really feel like I really can't believe I get paid to do my job. I get paid to share something I love with all of you. It's kind of like show and tell. I love interacting with students. I love having students in class. You know, we can interact with each other, ask questions. Unfortunately, we weren't able to do a lot of that besides with the forum. What I do want to say is I hope that you found this class helpful. I really did my best to try to set you up for success for next quarter. All of my videos, if you found them helpful, will always be on YouTube. You can always go back and check those out if you ever need a refresher. And I guess I do want to say, if you ever do see me out in public, please don't be afraid to come say hi. I would love to meet all of you, and maybe if everything clears up, I'd love to shake your hand, and I know I'd love to put some faces to all the names. But I guess before I get too emotional, let's go ahead and get on with our last lecture. So what we're going to do in this section is we're going to talk about General Conics. Mainly, what I'd like to do in the first part of this video is talk about why are these four shapes, the circle, the parabola, the, what else did we have? We had the ellipse and the hyperbola. Why are those called conics? Well, maybe based on the name and maybe based on the picture I have up on the board, they have something to do with a cone. In this case, actually an infinite cone. If you think about kind of two cones, one up and one down, they're kind of meeting at their tip. And they're infinite cones because they're going to go on in each direction infinitely. And it's not just a cone, but the intersection of a cone. The intersection of a cone and a plane. By plane, I mean like a piece of paper. So if we were to cut this infinite cone with a piece of paper, depending on the angle of that piece of paper or the angle of the cut, we're going to get one of our four conics. I guess instead of me attempting to draw this for you, let me just show you a picture. So if we were first going to cut this cone, let's say that is parallel, I guess parallel to the top and bottom of the cone. I know it's an infinite cone, but I'm kind of trying to we kind of think top and bottom. What kind of shape are we going to get? Well, we're going to get our first conic. We're going to get the circle. Pretty cool. Okay. Now, what if we instead make a cut with this shape? Okay, not, I guess, parallel to the top and bottom, but what if we make a cut so that it's parallel, I guess, to this line right here, parallel to this line? So in that case, it would intersect the cone. It would only actually intersect one of these two cones. So if it's intersecting it this way, kind of coming through here, it's not going to cross through the other side because it's parallel to this line. What kind of shape are we going to get there? Well, we're going to get a parabola. Pretty cool. So if we were to cut it this way, if it's parallel to this line, we'll have our frowny face parabola. If it's this way, we would have our happy face parabola. Pretty cool. And what would actually define the different parts of these shapes would depend on these lines. I know I kind of just drew one picture, but these lines I guess these lines here could have different slopes to them. Okay, well, what if we make a cut on this infinite cone, not straight through, not parallel to this line or to this line, but what if we were to cut it so it's going to cross through at an angle, and so it's going to go through both sides? What kind of shape will we get there? Well, in that case, we're going to get our third conic. We get our third conic. We're going to get the ellipse. Pretty cool. Pretty cool. Okay. Well, the only other one is, what if we were to cut this cone so that actually the piece of paper would cross through both of these? Well, the best way to think about that is if you had a piece of paper that was cutting straight up and down like this. What kind of shape are we going to get there? In that case, we're going to get our hyperbola. And what's actually really cool about this hyperbola is you can kind of think about these, it's kind of backwards for me, but these two lines right here, those are going to be like the asymptotes of our hyperbola. Pretty cool, pretty cool. So that's why they get the name a conic. They come from the intersections of this infinite cone. So it actually turns out there's a general equation for, I guess, a general conic. Let's go ahead and write that down. So general conics have the form, and you could discover this, if you were to kind of FOIL out all our shifted conics and kind of think about all the different possible combinations. But a general conic, if we were to expand, will have the form ax squared plus cy squared plus dx plus ey plus f will be equal to 0. And we need that a and c both not 0. If we could think for a second why a and c can't both be 0 at the same time. Well, if a and c are both 0 at the same time, we're actually going to get the equation of a line instead, which isn't one of our conics. Okay, so what we are going to do now is let's go ahead and write a general conic up on the board. And what we're going to do is when you're presented with a general conic, you may not know which one of the 4 it is. You're just going to take a little bit of massaging for us to figure it out. Here's our first example. Here we are presented with a general conic, and it's our job to figure out which one it is. Are you an ellipse? Are you a parabola? Are you a hyperbola? Are you a circle? I mean, tell me what you are! This conic is not in a great form. Half of the battle in math is having things in a good form so we can recognize what they are. So what do we need to do? We need to massage this thing. We're going to complete the square. That's what we want to do. So we're going to group the x pieces together, we're going to group the y pieces together, and we're going to put our constants together. Let's do it. Okay, 9x squared minus 36x. Okay. Oh, let's group our y's together. We'll do plus the opposite. So we have a minus 4y squared. Then we have if we do plus the opposite, we have a minus 24y. And then if you would like, you could leave the constant on the left-hand side. I personally like to put it on the right-hand side, so I'll add 36 to both sides. Okay, a little bit more work, Okay, what we want to do now is we want to factor a 9. Remember when we complete the square, we like there to be a coefficient of 1 in front of the x squared or a 1 in front of the y squared. So here we'll factor out the 9. We'll be left with a x squared minus 4x. Let's leave ourselves a little bit of room. Here we're going to factor out a negative 4. Okay, so we'll be left with a y squared plus 6y. Leave ourselves a little bit of room. And that'll be equal to 36. Okay, we're getting somewhere. Okay, now we got to think, what do we need to add here so this factors to a perfect square? Okay, well remember that we take the coefficient in front of x. So negative 4, we're going to cut that in half and we're going to square it. So that'll be a negative 2 squared. So you could add 4 right here if you'd like. I personally kind of like to leave the negative 2 squared here because it helps remind me how this will factor. Okay. But we got to be careful. I can't just add a negative 2 squared here. I can't just add a 4 inside these parentheses because I've changed the equation. I have to balance it, but be careful. I didn't just add a 4. We added a 9 times 4. So if we added a 9 times 4 here, we have to add it also to the other side. So we also need to add a 9 times a negative 2 squared on the right-hand side. Similarly, we have this 6 here. So we're going to take the 6, we're going to cut in half, and we're going to square that. So we'll get a 3 squared. So we'll add a 3 squared here, but be careful, we didn't just add a 3 squared, we actually added a negative 4 times 3 squared. We added it to the left, we got to balance it and add it to the right. So we have to add a negative 4 times 3 squared to the right-hand side. Okay? Okay, let's factor. Here we have a 9 times, what are we going to get here? This will factor to an x minus 2 quantity squared minus a 4. This will factor to a y plus 3 quantity squared. Okay, and what are we going to have on the right-hand side here? Let's see, we get a 36. Okay, we're adding a 9. Negative 2 squared is 4. 9 times 4 is 36. So we have 36 plus another 36. Here we have a negative 4 times 9. That's a negative 36. Okay, so conveniently, these 36 cancels. These 36 cancel. And we're just left with this. You might already be seeing which conic this is. It's starting to reveal itself. You see this minus here, I'm thinking this is going to be a hyperbola. Okay, but hyperbolas don't usually have, equal to a 36. Usually they're equal to 1. So to get this in that good form, we're going to divide everything by 36. Okay, so divide everything by 36. Really, we're just dividing both sides by 36. And on the left-hand side, we're distributing the 36 to each of the terms. Okay, how many times does 9 go into 36? I think it goes in 4 times. So we'll be left with an x minus 2 squared all over, 4? Minus 4 goes into 36 9 times. So this will be a y plus 3 squared all over 9. Be equal to 1. And here we have it. This is a hyperbola, and now we can gather all of its secrets. Let's do it. It's in a great form. Okay, so let's write it down. This is a hyperbola. Okay, let's see. Well, I'm subtracting 2 from x, so we're shifting the graph to the right 2 units. Okay, we're adding 3 to y, so we're shifting the graph down 3 units. So where will its center be? Its center, see, we're shifting it to the right 2 units. And down 3 units, so 2, negative 3. Awesome. Awesome. Okay, let's go ahead and sketch this. Okay, our center is at 2 and negative 3. Okay. Now let's think about what our A's and our B's are. Well, if this thing wasn't shifted away from the origin, if I kind of cover up this negative 2 and cover up this 3, if we cover up the negative 2 and cover up the 3, this would have x-intercepts. But of course, since it's shifted, the shifted one will have x and y intercepts, but the unshifted version will have x-intercepts. So this one is going to be facing to the left and to the right. So that tells us that our A, here our A squared will be equal to 4. So our A is 2. Okay, over here we have that our B squared will be equal to 3. So B squared will be equal to 9. So our B will be equal to 3. Now we can sketch that central box. Okay, so we'll need to go to the right and left 2 units. So here's 4. If we go backwards 2 units, we'll be at 0. Okay, so this is where one of the vertices will be for the hyperbola. This is where the other vertice will be. Okay, now we need to go up 3 units. So 1, 2, 3 here, and down 3 units. So here we'll be at negative 6. And now we can draw our central box. Okay. The asymptotes will go through the corners of the central box. Okay. And this is where one of our vertices will be. So here is a sketch of our hyperbola. Okay, let's write down some of the features. Okay, I guess we could start writing down the vertices. So I don't know, how about we'll call this one, I don't know, we'll call this one vertice 1, we'll call this one here vertice 2. So the coordinates of V1, the vertices. vertices. Let's see, V1 will be x coordinate of 0, y coordinate of negative 3, and the second vertice will be at x coordinate of 4 and a y coordinate of negative 3. Awesome. Okay, let's do our foci. Okay, I always kind of like to think about this right triangle right here. This right triangle right here. This will be our A in the situation. This will be our B, and this will be our C. So we have that C squared. I'm going to erase a little bit of this here, give us some more room to work with. Okay, so we're remembering the foci formula for a hyperbola. We'll have that C squared will be equal to A squared plus B squared. So our A was, our A was 2, so 2 squared will be 4. And our B was 3, so 3 squared will be 9. So we'll have that C squared will be equal to 13. So C will be equal to the square root of 13. Okay, for right now, I just say the foci, one of the foci will be here, in black. The other one will be over here. Okay, this will be, we'll call this one foci 1, we'll call this one foci 2. Okay, what will be the coordinates of these foci? Okay, so for foci 1, well, we're going to start at the center and then we're going to go left C units. So C is root 13. So we're going to start at 2 and then go to the left, the square root of 13. And the y coordinate will be negative 3. And then the other foci will start at 2 and then we're going to go to the right C units. So we'll go right root 13. So 2 plus root 13, and the y coordinate will also be negative 3. Okay, what's the last piece of information? Oh, we could talk about the asymptotes. Okay, let's write down the equation of the asymptotes. Okay, there's a couple ways you could do this. I usually like to think about the asymptotes not being shifted away from the origin. So if we have y is equal to, what will be the slope of this line? Okay, well, it looks like the rise is 3 and the run is 2. The rise is 3 and the run is 2. This will be a positive 3/2 slope. This will be a negative 3/2 slope. Okay, times x. This is if they weren't shifted. So I'm going to say, maybe I'll write unshifted. Okay, but now if they're shifted, let's see, we shifted it to the right 2 units and down 3 units. So we'll replace y with y plus 3. Now I'm shifting it down 3 units. Plus or minus, we'll have 3/2. Since we're shifting it to the right 2 units, we'll do x minus 2. Okay, oftentimes this is fine for you to write your asymptotes like this. I don't think these will be terrible to solve, so let's do it. Okay, I'm actually going to erase this picture right here, give ourselves a little bit more room to work with. So we have a y plus 3 will be equal to, we'll have the positive 3/2 times the x minus 2, and we also have the y plus 3 will be equal to the negative 3/2 times x minus 2. Okay, let's go ahead and distribute. I'm just going to put them in slope-intercept form. When possible, that's like, I don't know, my favorite form of a line. Okay, so we'll get a 3/2 x. When the 3/2 hit the 2, the 2's will cancel, so we'll just get minus 3. Okay, same thing over here. We'll get y plus 3 will be equal to negative 3/2 x. Now we're going to get a plus 3. Okay. So over here, let's subtract 3 from both sides. Okay, over here, we'll also subtract 3 from both sides. So we'll have that y will be equal to, looks like 3/2 x minus 6. And we'll have y will be equal to, looks like just negative 3/2 x. So those are the equations of our 2 asymptotes. So y equals 3/2 x minus 6, y equals negative 3 halves x. Okay. There might be one other feature that they may ask you about, or you may see some textbooks talk about, something that's called the transitive axis. So I'm not sure if I talked about this in the hyperbola video, but let's put that sketch up again just really quick. So let's see where we went down 3 units. Okay, just trying to sketch this really quick again. The line segment that connects the two vertices, this line segment here to here, this is sometimes for the hyperbola called the transitive axis. And it's just the line segment that connects the two vertices. Okay, what is the length of the transitive axis? Maybe I'll write that down. Length of transitive axis. Okay, well, this length here from the center to one of the vertices, that's what we called A. This will be A. So in general, the length of the transitive axis will be 2A. So in this situation, what our A was 3. So the length of our transitive axis for this example will be 6. Okay. So for us, it'll be 2 times 3, which will be 6. So that's something else that you might see WAMAP or the textbook asking for, the length of the transitive axis. Let's try this next example. I want you to pause the video, complete the square on x, complete the square on y, and reveal which conic we have here. Give it a shot. Okay, let's do it. Let's group all our x pieces together. So we'll have a 25x squared plus a 200x, plus we'll have a 9y squared minus a 36y. Okay, let's move the constant to the right-hand side, so we'll subtract 211 from both sides. All right. Let's factor out the 25 out of this first set of parentheses, so we'll get a 25 times, let's see, 25 goes into 200 8 times, so x squared plus 8x. We'll leave ourselves a little bit of room. Plus, let's factor out that 9. We'll be left with a y squared minus, what, 4? 9 goes into 36 4 times. We equal to negative 211. Okay, let's complete the square on x. So we'll take that 8, we'll cut it in half and square it. So we'll want to add a 4 squared inside the parentheses. But really, we added a 25 times 4 squared on the left. So we'll need to make sure to add a 25 times 4 squared on the right to make sure everything's balanced. Okay. Here, to complete the square on y, we'll take the negative 4, cut it in half and square it. So that'll be a negative 2 squared. So we'll add a negative 2 squared inside the parentheses. So, but really we added a 9 times a negative 2 squared on the left. So we're going to need to add a 9 times a negative 2 squared on the right. All right, now we're cooking. All right, so we're going to get a 25 times, this will factor to an x plus 4 squared, plus a 9, this will factor to a y minus 2 squared, and that's going to be equal to, I don't know, maybe the right-hand side is the job for a calculator. I don't want to do too much in my head, make a mistake. I don't know, adding's hard. Okay, plus a 9 times a 4. Okay, so I'm getting a 225. And maybe already you're starting to to figure out which conic this is. I don't know if you can smell it through the screen, but over here, this smells a lot like an ellipse. I'm getting wafts of ellipses over here. Okay, but ellipses usually have a 1 on the right, so let's divide both sides by 225. Let's divide both sides by 225. Now on the left-hand side, I'm distributing the 225 to both pieces, or both terms. Okay, 25 goes into 225. Let's see how many times. That'll be 9 times. X plus 4 squared all over 9. Plus, let's see, how many times does 9 go into 225? Let's see, 225 divided by 9. It's like 25 times. So this will be a y minus 2 squared all over 25, and that'll be equal to 1. And now we have this beautiful form of a shifted ellipse. Now let's write down, let's draw a rough sketch and write down all its features. All right, this whole time, this conic was an ellipse. It's like, why didn't you just tell us from the beginning? Why did you just tell us from the beginning? It was being sneaky. You know, it's like it's playing hide and seek or something. Okay, so we have an ellipse. Let's write the equation right here, just so I can go back and refer to it. Leave ourselves some whiteboard room. Okay, let's figure out its center. Okay. So we're adding 4 to the x, so that's going to shift the ellipse left 4 units. We're subtracting 2 from the y, so that shifts the graph up 2 units. So our center will now be at -4 and 2. All right, what else do we need to know? Well, notice that the y piece is being divided by 25, the x piece is being divided by 9. This is going to be stretched much more in the y direction. I don't know about much more, but it's going to be stretched more in the y direction than in the x direction. So remember, for ellipses, the a is always the bigger number. So here we have our a squared will be equal to 25, so our a will be 5. This is our b squared, so b squared will be 9, or our b will be 3. Okay, let's sketch this. I'm gonna record these right here. Our a is 3, or sorry, our a is 5, and our b is 3. So our center is at what, -4, 2. -4, 2. Here's our center. Okay. Our a is 5, so I need to go 5 in the y direction from our center, so we'll go up 5 units. So let's see, 5 and 2, that's 7. So here will be one of our vertices. And then we need to go down 5 units, so 1, 2, so I think we'll be at -3. Okay, and we need to go 3 units to the left and right of our center. So here at 1, we'll have a point here. We need to go left 3 units. So here's -7. So here, you know, it's not perfect, it's hand drawn, but here's a rough sketch of our ellipse. Okay, let's see, what could they ask us? They could ask us for the vertices. So here's one vertice. So we'll call this one V1. Let's call this one here V2. So the vertices. V1, that'll have coordinates, what, -4, 7. And V2, -4, -3. Okay. And what else could they ask us? Well, we're probably going to want to look for the foci. Okay, so when we're trying to, remember when we're trying to find the formula for the foci, the picture I always have in my head, so if we have an ellipse, okay, I think about this string here. If we're drawing the ellipse, the length of the string is always the length of the major axis. That's what we discovered. The length of the string will always be 2a. So conveniently, I put the string at a spot where, you know, I have kind of cut the string in half. If the length is 2a, then this will be a and this will be a. The length from the center to a foci is what we call c. The length from the center to, I guess, the top of the minor axis will be b. So we have this beautiful right triangle here. This reminds me that the formula, we have that a squared is equal to, looks like b squared plus c squared. Or if we solve for c squared will be equal to a squared minus b squared. Okay. For a lot of these things, I'm not very good at memorizing things. If I can just have kind of simple pictures in my head, I can remember things a lot easier. Okay, so we have that c squared. Let's write that up here. We have that c squared will be equal to a squared minus b squared. Okay, our a squared is 25. So c squared will be 25. Our b squared is 9. So 25 minus 9. 25 minus 9, I think that'll be 16. So we'll have that c will be the square root of 16, or c will be 4. Okay, so if we go up 4 units, 1, 2, 3, 4. Okay, this is where one of our foci will be. 1, 2, 3, 4. This is where the other foci will be. We'll call this, call this foci 1, foci 2, focus 1 and focus 2. Let's see, so focus 1 will have coordinates negative 4, 6. And focus 2 will have coordinates negative 4, negative 4, negative 2. Beautiful. Okay. What else should we know? Maybe the length of the major axis? I'm trying to think of all the things I could ask you. Length of major axis. Okay, so this is the major axis here. It's always the same thing as 2a. Okay, what was our a? Our a was 5, so this will be 2 times 5, or that'll be 10. That should make sense. From here to here is 7, from here to here is 3, 7 and 3 is 10. We could also ask the length of the minor axis. Okay, that'll be 2b. Okay, our b was 3, so 2 times 3, that'll be 6. Okay, that should make sense. Let's see, here's 1, 1. Well, this should be a negative 1. I don't put a 1 here, but a negative 1. So negative 1 to negative 7, this distance here is 6. Beautiful. Okay, oh, what about eccentricity? Eccentricity, that's E. That's E, and that's defined, well, this is an Euler's number, E for eccentricity. This is defined to be the ratio of C over A. Our C is 4. Maybe I'll put that over here. Maybe I should have wrote that over here. Our C is 4. Okay, C is 4, and A is 5. So, what? 4, what is 4? That's what, that'll be 0.8. 0.8. So, I don't know, this isn't like, remember if the eccentricity is really close to 1, it's really, it's more elongated the more the eccentricity is close to 1. I know this isn't like super duper elongated, so I think 0.8 feels pretty good for the eccentricity of this ellipse. Let's try this next example. Go ahead and pause the video and see if you can discover which conic we have here. Okay, let's do it together. In this example, we could almost, without doing any work, we could probably already see which conic this has to be. Notice I have a y squared, but there are no x squareds. The only conic that we have that only has an x squared or a y squared is a parabola. So I'm predicting right off the bat that this is going to be a parabola. Okay, let's go ahead and group our y pieces together. So we'll have a y squared minus a 4y. There's nothing to factor off the y squared, so I'll just already leave myself some room here. This is going to be equal to, I guess, plus 8x. And let's add 36 to both sides. All right. Let's complete the square on y. So we'll take that -4, we'll cut it in half, and we'll square it. So we'll want to add a -2 squared inside the parentheses. Okay. So in this case, there's a coefficient of 1 in front of these, in front of the set of parentheses. So we really did add a -2 squared this time to the left. So we'll want to add that to the right. This will factor to a y minus 2 squared plus an 8x. This will be a 36 plus 4, so that'll be a 40. Okay. Well, I have this y minus 2 squared piece, and now I'm just trying to kind of think to myself what the general form is for a parabola that has this y being squared. It'll be a y minus k squared will be equal to a 4p times an x minus h. So I'm going to want to move the x pieces to the right. Y minus 2 squared, that'll be equal to a -8x plus 40. Okay, I want to know how it's been shifted left and right, so I want to know what's acting directly on x, or what's being added or subtracted directly from x. So I need to factor out this -8. So y minus 2 squared, that'll be equal to a -8, and we'll be left with a x minus 5 when we take a -8 out. All right, here we are. So we have a parabola. And here we might already be able to tell the orientation. Since the y is being squared, that's either going to be a parabola opening up to the right or to the left. Since there's a negative right here, it's going to be opening up to the left. This is actually going to tell us that that p-value is going to be negative. This is a parabola, and it's going to be opening up to the left. Okay, let's write this. Y minus 2 squared is equal to a -8x minus 5. Okay, let's sketch this. Okay, I guess we should remember the general form. Let's also write this down. Okay, so let's figure out what our p is. Well, notice here that I guess you could either factor a 4 out of the -8, or you could say that -8 is equal to 4p. If we divide both sides by 4, we'll get that p will be -2, so that's a good thing to write. Our p will be -2. Okay, what will our vertex be? What will be our vertex? Well, we're subtracting 2 from y, so that's going to shift us down 2 units, so the y coordinate will be 2. We are subtracting 5 from x, that's going to shift it to the right 5 units, so the vertex will be at 5, 2, and our p is -2. Okay, let's do a rough sketch. Okay, our vertex is at 5 and 2. Here's our vertex. Okay, our p is -2, so that means I'm going to go to the left 2 units of the vertex. So here's 3. So here's our focus. I'll put a little f here. Maybe I'll actually put the f here. And to get to our directrix, we'll go right 2 units from the vertex. So 7, here is the directrix. Okay, so to figure out the width, remember that we want to think about the length of the focal diameter. We start at the focus and we'll go this way 2 units and this way, this way 2p units and this way 2p units. And when I'm saying p, I'm meaning absolute value. So the absolute value of 2p will be 4. We'll go up 4 units. So that'll be 6. We'll go down 4 units. So -2. So this will be a point on our parabola. And this will be another point on our parabola. Again, remember that the definition, the geometric definition of a parabola is all the points that are equal distant from a focus, a dot, and a line, which we call the directrix. So just to write this distance right here, this is, I guess I'll write the absolute value of P. This distance here is P. This distance here is also P. This point is on the parabola because the distance from here to the focus will be 2, and the distance from the vertex, or this point here, to the directrix will be 2. So this is a point on the parabola. Okay, well, the distance from here to here, this is 2p. This is 2p. Why is this a point on our parabola? Well, if the distance from here to here is 2p, well, the distance from here to here, I hope you see, is also got to be 2p. And similarly down here. So here we have our parabola. I should say absolute value. Okay. So what else do we need to know here? We got the vertex. We have what our p-value is. Let's write the equation of the directrix. Okay, that's the equation of this vertical line. The equation of this vertical line will be x equals 7. And the length of the focal diameter, is going to be the absolute value of 4p. It's just this physical length here. In this case here, it's going to be 8. Okay. And I think that's everything we need to know about this parabola. Here's our next example. Pause the video and give it a shot. Okay, let's do it together. All right, let's group our x pieces together. So we'll have an x squared plus an 8x. Okay, I won't have to factor anything off the x squared, so I'll just already leave myself some room. And we'll have a y squared plus a 4y. I don't have to factor anything off of y squared, so we'll leave ourselves some room. And let's subtract 11 from both sides. So this will be equal to a negative 11. Okay, let's take the 8, cut it in half, and square it. So we'll get a 4 squared. So we'll add 4 squared inside the parentheses. There's just a coefficient of 1 out here, so we really did add 4 squared to the left. So we'll add 4 squared to the right. We'll take this 4, we'll cut it in half and square it. So we'll get a 2 squared. So we'll add a 2 squared here. We really did add a 2 squared on the left, so we're adding a 2 squared on the right. All right. Let's see what we get here. All right. Well, this is going to factor to what? An x plus 4 squared. This will factor to a y plus 2 squared. And that's going to be equal to, what is this? This is negative 11 plus 16 plus 4. So what, that's 20. 20 take away 11. 20 take away 11. That's going to be 9. All right. Well, I don't even think we have to go any further here. I hope we see here that this is a circle. This is a circle of radius 9, and its center, well, its center will be at negative 4, negative 2. All right. This is a circle. I guess if you wanted to, if you divided both sides by 9, I guess you could say that this is an ellipse that has both an A and B value of 3, or we could just say it's a circle of radius 3. Okay. So let's write that down. We have a circle. Its radius is going to be the square root of 9. So the radius will be 3. Its center. The center, okay, well, we're adding 4 to x, so we're shifting it left 4 units. And we're we're adding 2 to y, so we're going to be going down 2 units. So the center will be at -4, -2. All right, let's give it a quick sketch. I think we have enough room. So here's -4, -2. Okay, we need to go up 3 units. So what? 1, 2, 3. So we'll mark this point. We'll go down 3 units. We'll go right 3 units. We'll go left 3 units. So while this is hand drawn, it's hand drawn, but this is supposed to be a perfect circle. It's a circle of radius 3, center at -2, and a radius of 3. Awesome. So it turns out that with the general form of a conic that we put in the beginning of the video, there are actually 3 degenerate conics that we could get. So 3 things that could possibly show up that are not ellipses, that are not parabolas, that are not hyperbola, that are not circles. We can sometimes get 2 lines. Okay, a set of 2 lines. We could also get a point, just a single point. And we could also get no graph. Okay. Let's see an example of each of these. All right. So let's say we have x squared minus y squared minus 10x plus 10y is equal to 0. All right, let's say we try to figure out what conic this is. Let's go ahead and group our x's together. Let's group our y's together. So we'll have a -y squared plus 10y. Okay. This x squared minus 10x, there's nothing I need to factor out front. However, I need to factor this -1 out. So we'll factor out a negative. And what are we going to be left with? We'd be left with a y squared minus 10y. All right. Over here, we would need to take that -10, cut it in half, and square it. So we'd want to add a -5 squared here on the left-hand side, which means in this case, we'd be adding a 1 times -5 squared to the right. Okay. Over here, we'd be taking this -10, we'd be cutting that in half and squaring it, so we're also going to be adding a -5 squared here. But in this case here, we're not adding a -5 squared on the left-hand side, we're actually adding a -5 squared. So we're adding or I guess you could think subtracting, let's just do a negative. We're adding a -5 squared. All right. Let's see what we get when this cleans up. All right, over here, we're going to get a x minus 5 squared. Okay, it's going to be minus a y minus 5 squared. And that's going to be equal to, well, we're going to get what? 25 plus a -25. We're just going to end up getting 0 on the right-hand side. Well, you might almost think this kind of looks like a hyperbola because there's a minus here, but there's a 0 on the right. And we can't divide both sides by 0 to make this a 1. Remember, we can't divide by 0, so this is something different. And how are we going to figure out what it is? Well, I think what we can actually do here is we could solve for y. So let's try to do that. Let's see if we can write this as y as a function of x if possible. So x minus 5 squared, we're going to add this piece to both sides. So this will be equal to a y minus 5 squared. Okay, let's square root both sides. Okay, when we square root both sides, we're solving for y. We'll need to have our plus and minus. So we'll have a y minus 5 is going to be equal to a plus or minus x minus 5 on the left. All right, let's see what we get. Okay, what is this saying? Well, we could have that y minus 5 could be equal to the positive x minus 5, or we could have the y minus 5 could be equal to the negative x minus 5. So we'll have, let's add 5 to both sides. Okay, so it looks like we're going to get what? Y equals x. And over here, we'll have a y minus 5. We need to distribute this negative into the parentheses. So this will be equal to a negative x plus 5. Let's add 5 to both sides. So we have that y will be equal to a negative x plus 10. Okay, what do we have here? Well, that conic, the general conic we have on the board, is a set of 2 lines. So in this case, you could kind of almost think, how is this the intersection of the cone? Well, if we think about the cone, this is if we were to cut it like straight up and down, and you would cut it right through the tips. So you would just kind of get those 2 lines. It'd almost be like we're just recording almost like the asymptotes, I guess, if you want to think of a hyperbola. So what would this look like? We have the equation y equals x. So y equals x. That's this line here. Okay, y equals negative x plus 10. We have a y-intercept of 10. 10, it has a negative slope. Over here we'll have another 10. So this is the equation y equals negative x plus 10. And this one right here is y equals x. Cool. All right, so we could possibly get a set of 2 lines. Okay, what else could we get? Let's do another one. As an example, let's say we have 4x squared plus y squared minus 8x plus 2y plus 9 is equal to 0. Okay, let's maybe attempt to figure out which conic we have here. Let's group our x's together. We'll group our y's together. And maybe we subtract 9 from both sides. Let's factor out this 4. And there's nothing to factor out here. All right. Okay, over here, we would need to take the negative 2, cut it in half, and square it. So we'd want to add a negative 1 squared. Okay, over here, we would take the, let's make sure I don't forget to add it to the other side. We added a negative 1 squared, or really just a 1 inside these parentheses, but we really added a 4 times a 1. We really added a 4 times a negative 1 squared. Over here, take the 2, cut it in half, and square it. So here we'll add a 1 squared. Okay, so we really are adding a 1 times a 1 squared. Okay, so let's see what we get. Right, so we will have a 4. This will factor to a x minus 1 squared. This will factor to a y plus 1 squared. And what will that be equal to? Well, what do we have here? This is a negative 9, a negative 9 plus 4 plus 1, negative 9 plus 5, what do we get? What is that? Negative 4. We get negative 4. Okay? Well, I mean, you might almost be kind of, I guess, tempted to think this might be an ellipse. I mean, the problem is we have this negative 4 over here. I guess, for fun, I guess we could divide both sides by 4. We'll see here, we can almost, maybe you don't see it, or maybe you do see it. We already do have kind of a contradiction here. This will be a no graph situation. I'll show you why. So I didn't actually have to divide by 4 to see this. But let's think right here. Well, I'm taking some number. I know this is x minus 1, but it's being squared. This is some positive number. And we're adding it to, well, we have some sort of number that's being squared. It's positive. It's being divided by a positive number. So we're taking something that's positive, and we're adding it to something that's also positive, and we're saying that's being equal to a negative. Well, a positive plus a positive is a positive. A positive is not equal to a negative. So we have a contradiction here. So what we have is no graph. No graph. Okay. So there is no value or no set of x and y that you could plug into this equation right here to make it be equal to 0. This is never true. This is never true. We get no graph. Okay, let's do one more. Okay, let's say we have x squared plus y squared minus 2x plus 4y plus 5 be equal to 0. Okay. Let's attempt to complete the square to see if we can figure out what conic this might be. Okay, so what we'll have is a x squared minus 2x. Oh, my poor pumpkin outside. Poor little pumpkin. Okay, we'll group our x's together. Let's group our y's together. And let's subtract 5 from both sides. Alright, if we're going to complete the square here, we're going to take that negative 2, we'll cut it in half and we'll square it. So we'll add a negative 1 squared here. So we added a 1 times a negative 1 squared. So, alright. Over here we'll take the 4, we'll cut that in half and square it. We'll get a 2 squared. Okay, so we want to add a 2 squared here. So we'll be adding, we added a 1 times 2 squared on the left. We're adding a 1 times 2 squared on the right. So let's see what we get. This will factor to a x minus 1 squared plus a y plus 2 squared. And what do we have over here? Well, this is a negative 5. A negative 5 plus 1 plus 4. So that's a negative 1 plus 1. We get out a 0. We get out a 0. Well, let's think about this here for a second. This almost looks like it could be an ellipse, or maybe you might be thinking a circle, but on the right-hand side, it's equal to 0. You could almost think that this is a circle of radius 0. You might think this is like a circle of radius 0. Okay, well, a circle of radius 0, that would just be a single point. Notice here there's actually only one there's only one ordered pair that solves this, so there's only one combination of x and y together that will make this equation true, and that's if x is equal to 1 and if y is equal to negative 2. This is just a point. And I guess if you are thinking in terms of the conics, this would be where the plane just intersects where the two tips of the conic meet. Okay, so we can possibly get a degenerate conic that can pop up. So these are all the examples I have to show you. Let's go ahead and conclude our last video with a quick animation in Desmos. We'll see you there. Okay, here we are in Desmos. Let's go ahead and type in the general equation of a conic. Let's make some sliders. Let's build some animations. Let's have some fun. Okay, so a general conic really just has multiples of x squareds, multiples of y squareds, multiple of x's, multiple of y's, and a constant term. So we need to add all those pieces in. So we'll want a multiple of x squared. We'll also want to add in a multiple of y squared. For some reason, I don't know why the book doesn't like to use capital letter B. It uses capital letter C. There's probably some reason, so I'll just stick with the notation the book uses, but these are just arbitrary letters. So we'll have a multiple of y squared. We'll also want a multiple of x. We'll want to add in a multiple of y. And we'll also want to add in a constant term, and we'll have those all equal to 0. So automatically, Desmos is asking whether we want A, C, D, E, and F to be sliders. We don't see any F here, but Desmos only displays 4 at a time. So if we want these to be sliders, which we definitely do, we'll just go ahead and click all. So now A, C, D, E, and F, we can control what these coefficients are with these sliders. If you want to change the range, so automatically they're setting all of these constants to be 1, and I can change their values from -10 to 10. If you just click in one of these boxes, you could have a range from, I don't know, -20 to 30 if you wanted to, or whatever you'd like. You can change it here. But for right now, I'm just going to kind of play around. We'll just we'll let A go from -10 to 10. Okay, let's see if we can play around with these numbers to, I don't know, get any of our conics, maybe some degenerate conics. And I should also note that there are actually conditions for these A, C's, D's, E's, and F's to get a specific conic. There's a condition that must be met to get a parabola, a condition that must be met to get an ellipse. We're not going to do that in this video. We're just going to kind of play around to see if we can just tweak these a little bit to figure out how to get one of our 4 conics. Let's first try to see if we can get a parabola. Actually, the first thing I'm going to note here is notice that we're getting no graph at all. So if I kind of zoom out, notice that there's no graph anywhere. Bummer. This must be that degenerate conic where we get no graph, which just means that if all of these coefficients are 1, there will be no x and y values which will satisfy this equation. Bummer. But let's see if we can get a parabola. Okay, so if we have a parabolas just either have x squared pieces or y squared pieces. They can't both be there at the same time. So how about we get rid of the x squared piece? So let's make a 0. So if we let a be 0, okay, if a is 0, notice that we're getting a parabola. Even if I zoom out, you may think that was an ellipse. You don't know how it closes, but if we zoom out and move, this is definitely a parabola. This is definitely a parabola. Okay, if it was an ellipse, I would need an x squared piece to stick around. So we have a parabola, and it's opening up to the left. Now it shouldn't be surprising that it's opening up to the left or to the right, because the x squared piece is gone. I just have a y squared piece, and remember those are the ones that open up left to right. Now I see that C is 1 here, so C is positive, but you shouldn't generalize because C is positive in this case that it's opening to the left or the right. It really does depend on all 4 or all of these numbers here, but at least what we got here is what we should note is that if we make A 0, we'll just have a y squared piece that sticks around, and we're going to get a parabola that opens up to the left or to the right. And we can change that parabola. Looks like if I let C be bigger, we're getting this skinnier parabola. And then if we move C to be it's a little bit smaller, going into be negative. Well, what if C is 0? Well, here we're getting a straight line, which actually shouldn't be too surprising, because if A and C are both 0, we won't have an x squared piece, we won't have a y squared piece. We'll just have a multiple of x, a multiple of y, and a constant term. This is just the general, I guess what we call the standard equation of a line. Okay. So let's see. So let's let C be negative now, and now when C is negative, it looks like we're getting in this case, a parabola that's opening up to the right. What happens if we change these just for fun? Oh, looks like these can also make it be opening up to the right or to the left. But again, all I really know here is just because I have a y squared around, that'll be opening up to the left or to the right. So pretty cool. Awesome. Pretty cool. All right, well, we have a parabola that's opening up to the left or to the right. How could we get a parabola that's opening up or down? Well, we want to keep x squared around, and we want to get rid of y squared. So let's keep c around. I'm sorry, no, let's get rid of c. Let's get rid of c, and let's let a be non-zero. So now we're getting a parabola that's either going to open up or down. In this case, now we're getting a frowny face parabola. Now we're going to get a happy face parabola. And I think these values here could also change whether it's happy or sad too. Pretty cool, pretty cool. All right, what other conics could we get? What other conics could we get? Well, we could get, how about, let's try to get an ellipse. I think if we need an ellipse, we at least need A and C to be positive. So let's let A be positive and C be positive. Look, now we're getting an ellipse. We're getting an ellipse, pretty cool. So if I change the C value, looks like that's kind of, I don't know, stretching it out in the Y direction a little bit more. Again, it still does depend on all four of these values, but just kind of playing around a little bit. So if I go make it smaller, at some point we have a circle here. At some point we have a circle. Pretty cool. But there, cool, we get an ellipse. What do these do? Shrink it. Look, at this point we might just have like a single, so if it's kind of shrinking the radius, it's not showing it, we might just have like a single point right here. I don't know if I zoom in if we can see it. Again, E is 0.1, so I mean I don't really know. It might be, I don't really know exactly the value of E to make it an exact point or no graph. Desmos doesn't really do a good job of showing a single point, but here we are. We're getting an ellipse. Okay, let's see if we can get a hyperbola. Okay, if we have a hyperbola, we're probably going to need at least A or C to be negative. So let's let A be negative, and let's see what happens. So let C be a little bit bigger. Okay, and what happens if we kind of let A start to get negative? So it looks like we're getting an ellipse that's starting to stretch out, and then all of a sudden, once A starts to become negative, now once it starts to become negative, we're getting an ellipse. I'm sorry, we're getting a hyperbola. We're getting a hyperbola. For some reason, I almost think that a hyperbola is almost like taking an ellipse and kind of turning it inside out. So if we let A get closer to negative, so now we have an ellipse. Now all of a sudden, we get I guess if A is 0, now we're going to get a parabola. It's almost like the transition from an ellipse to a hyperbola. It goes ellipse, parabola, hyperbola. Ellipse, parabola, hyperbola. So here's the parabola, and then here's the hyperbola. Pretty cool. Whoa. Whoa. So A is negative, C is positive. Okay, what if we do it the other way around? What if we let C be negative? Now we have, I don't know, we're getting a different hyperbola. Pretty cool. Pretty cool. Ellipse, ellipse, parabola, hyperbola. Whoa, that is pretty awesome. So, can we possibly get a set of those two lines to show up? Let's see, what can we do to make that happen? Oh, if we bring these closer, there's probably this kind of part where those are kind of just kissing. I don't know. There's probably some sweet point here we could do here to get those set of two lines. I don't know. You could play around with this at home. Again, there are conditions. There are conditions that could be met. That can be met to guarantee that you have a hyperbola. Oh, look! Oh, there we got it. There we got it. Pretty cool. Just messing around. Oh, not quite. I don't know. Looks pretty close. There are conditions for these coefficients to get one of these four shapes, but here we're just kind of having fun with Desmos. So I highly recommend, play around with this yourself, and make sure to have fun. Always be smiling. All right, well, that's all I have for you for this lecture here. I guess this is all we have for Math 141. Again, it was a pleasure being your teacher. Make sure to have a great summer. For those of you who are going on to 142, I wish you the best of luck. And for those of you who are going on to calculus, I hope a lot of you will go on to calculus. Calculus is really one of the most beautiful subjects. I'd say the discovery of calculus was really one of the top 5 discoveries of humankind. I wouldn't say just just in math, but without calculus, we couldn't do engineering. Without engineering, we really wouldn't have all the technology we have now. So, here we are in pre-calculus, warming up for calculus. So, anyway, take care, everyone, and we'll see you later. Bye-bye.